screen at this point. And so, like I said, we're going to start with chapter 7 today, and chapter 7 is a pretty extensive chapter. It is the largest chapter that we're going to deal with in this particular course. It's got all of elimination and all of substitution reactions in that chapter, along with naming alkenes. So what we're going to do is we're going to start off with substitution reactions, and the specific substitution reaction we're going to start off with is an Sn2 reaction. And what I want to point out is, what is Sn2, or what is this sort of naming, or what does this word mean, or what does this symbol mean? So Sn2 means, this one is the hard part. So I'll answer the hard part for you. This one is substitution. Right? That was the hard part, right? Everybody? Can I get an F in chat for the hard part? All right. Anyway, this is the easy part. The easy part of this is these two things. The N stands for nucleophilic. 2 L's, right? Nucleophilic. So what we mean by this is a nucleophilic substitution reaction. It's going to be a situation where a nucleophile attacks a substrate, and this is what prompts the substitution to move forward. The 2 refers to the kinetics of the reaction, and this means it's bimolecular. And this is an important concept, because bimolecular helps you remember how the mechanism of the reaction actually takes place. Ultimately, what this means is that it requires 2 species. It requires 2 species for the reaction to occur at the same time. And so what we want to do is kind of break this down and see what all this business means. But before we do that, we want to kind of just talk about what species will be the substrate that is involved in this reaction. And so essentially what we're talking about are, these are alkyl halides. So we've already talked about naming alkyl halides. So what, if we were to remember correctly, this one would be 2-chlorobutane. And if I were to actually remember that this is a chiral center and specify the chirality, I would say this is the first priority, this is the second priority, this is the third priority, the fourth priority is in the back, so the arrow goes this way, that's counterclockwise. So specifically, this is S2-chlorobutane. And so that's definitely something that's going to be on the exam, and so I just wanted to kind of give you a little bit of a reminder. So we've already named haloalkanes, we've already named alkyl halides, and so we're going to kind of move on from that point. Here's what we need to know about Sn2 reactions. What if we recall the hybridization of this particular molecule, or this particular carbon, is sp3. If I were to think about something that is attached to a benzene ring, like this, or even a double bond like this, then these are both sp2 hybridized carbons. And at the end of the day, there's an important concept that you're going to need to remember in the course, and that's that Sn2 reactions don't occur at sp2 carbons. So really what we're going to be focusing on is sp3 carbons and the reactions that happen there. Now, in general, the chapter talks about 2 different situations. The first situation it talks about are substitution reactions. And the general idea for a substitution reaction is when you have an alkyl halide. It reacts with some sort of nucleophile. And we're going to talk a little bit more about what nucleophiles, well, we already know what they are, but we're going to talk about what makes a good one. And the chlorine or the halogen gets substituted for the nucleophile. Right? This is essentially what a substitution reaction is, and whether or not this happens bimolecularly or unimolecularly determines whether or not it's Sn2 or Sn1. An elimination reaction is essentially the same substrate as a starting material, but instead of having it react with a nucleophile, it reacts with a base. And instead of substituting, we form a double bond. The base gets protonated and we still have the chloride hanging around. And so these are the two essential reactions that we're going to discuss in this chapter, but there's a lot of details that are involved with these reactions. And so what I would like to get through today, my goal for the day is to get through Sn1 and Sn2 and E2 reactions. All right. So what's going on with this? If we think about why a reaction like this might undergo a substitution, or why is it reactive? I want to remind you, because this is going to be something that you're going to have to do on the test, to examine this substrate. So I'm going to use the word substrate to refer to the haloalkane, to refer to the alkyl halide as the reactant of all of these particular reactions. So the word substrate is going to be the thing that I use to describe this particular species. In other words, it's going to be generally a haloalkane, but at the end of the day, all it really needs is a good leaving group. And we'll talk about good leaving groups next. But what I want to do is I want to go back and talk about, well, what's going on with this substrate and why is it going to be reactive? Why does it do substitution? Well, remember that the chlorine has got a partially negative charge. And that partially negative charge will then, of course, leave the carbon partially positive. And if I talk about what a nucleophile, remember a nucleophile is going to react with it. The nucleophile is either got a pair of electrons, maybe it's got a negative charge. Oftentimes it actually does. But at the end of the day, the electrons or the negative charge is going to be attracted to the carbon that's partially positively charged. And that's what's going to make this substrate reactive. So what about this component here, though? And this is what I was just mentioning a second ago. That component has to be a good leaving group. One of the skills that you're going to have to develop is identifying what a good leaving group is. And a good leaving group is anything that is stable by itself. Now, if we think about identifying species that are stable by themselves, we've already got some practice doing this. So if we think about back to chapter 3, when we talked about acids and bases, we thought about something like HCl in terms of its acid-base reactivity, and to try to determine whether or not this was a strong or weak acid. Well, we said to ourselves, we can figure out that HCl is a strong acid because chlorine is very stable, or chloride is very stable, Because chlorine is very electronegative, and when it has a negative charge, it's stable because of the, we personify it and we say that because of chlorine's desire to have extra electrons. And so that was one of the things that we did. One of the other, what else did we do? So that was the atom consideration. We took a look at resonance. We took a look at induction. And we took a look at the hybridization of the carbons that are involved. And so that all of these things kind of lead to the idea of, well, what's a good leaving group? And so at the end of the day, based on that analysis, we say that a good leaving group, they're going to be conjugate bases of strong acids, right? That hopefully right now what that's doing is that's making some sense. Because if it's a strong acid, that means that the conjugate base is stable. And if I have something on a substrate that is a good leaving group, then that means that when it leaves and a nucleophile replaces it, that it's going to be stable, right? So a good leaving group would be a conjugate base of a strong acid. Karen's back. And that way we would understand that it's going to be it's a good leaving group. It's going to be stable that way because it's alone. So what are some of the conjugate bases of strong acids? What's up, Carol? Hold on a second. Go ahead and type your question into chat. So while the question in chat's being typed, what I'm going to do is I'm going to draw the structure of some. So the question is asked, are all halides good leaving groups? The general answer to that question is yes, with one exception. So that brings me right into the next little bit. If I think about the halogens that are HI, or the halogen-based acids, HI, HCl, and HBr, all three of these guys are strong acids. They have pKa's of, like, this one is -11, this pKa is -9, this pKa is -7. But if I compare it to HF, we should realize that HF is a weak acid. It has a pKa of 3. So it's quite a bit weaker than the other three halogens. And so while these guys are all strong acids, which makes all of these halogens fantastic leaving groups, the fluorine is not a good leaving group. And so that was a great question to ask. Does that help? Does that clear it up for you? All right. So the next part is, the next thing I want to draw is what else are some good leaving groups? This one is going to be pretty popular because we're going to be using it quite a bit. This is a sulfonic acid. So there's a sulfonic acid. Its pKa is around -3. And so at that point, -3 is a pretty good, hold on a second. That's low enough of a pKa in order for it to have in order for it to be strong acid.
Professor, what's on top of the sulfur?
Oh, these are oxygens, so excuse my sloppiness. So the conjugate base of this thing would involve not having the hydrogen attached to it, and instead of a bond, it's got a lone pair and it's negatively charged. So why is this thing going to be particularly stable? This thing is stable because of resonance, right? There's resonance involved with this negative charge here. What are some other good leaving groups? I think the last one that we want to talk about is this acid. We should all be familiar with hydronium ion. Hydronium ion has a pKa of around -2. So the conjugate base of that would involve the loss of this proton and the 2 electrons there. So the water, in other words, what I'm trying to get at is water is a fantastic leaving group. We really need to understand that when I think about water itself, its pKa is 15.7. And so what does that mean? That means that hydroxide is not a good leaving group. It's not a good leaving group. And so one of the things that we're going to really get to be familiar with is this idea that if I want to make something that is an alcohol, in other words, something that has hydroxide on it, into a good leaving group so it can do a substitution or an elimination reaction, I have to protonate it first to turn it into a water that's attached. Oh man, there we go. I have to turn it into a positively charged water group so that it is water that's leaving instead of hydroxide. And ultimately, that's going to be a pretty common theme when it comes to substitution and elimination reactions. All right, and so what I want to do is I want to just pause for a beat and see if there's any questions about anything so far. All right. And so what we want to do is we want to, the next thing I want to do is talk about the classification of different haloalkanes or alkyl chlorides or alkyl halides. Just like we talked about when it came to carbocations, we've got this idea that I've only used the same idea of primary, secondary, and tertiary to describe different haloalkanes. And the reason that that's going to be important is because the different substrates, whether they're primary, secondary, or tertiary, favor different types of reactions. And one of the most difficult challenges in this chapter is me giving you a substrate and a reagent and saying to you, what is the most likely reaction that will occur? And you having to examine both the substrate, one of these guys, and the reagent, whether or not it's a nucleophile or a base, because recall that elimination reactions require bases, substitution reactions require nucleophiles. It's me giving you these two pieces of information and you deciding what the mechanism is and then what the likely product is. And so there's a lot of considerations that are involved, and this is where it starts. It starts at the substrate level, identifying the substrates as either primary, secondary, or tertiary. So what I want to do is I want to write a couple of examples down and think about something like this. So let's take a look at this one, and I want you to be ready to write in the chat bubble, in the chat window. Is this substrate here, is that primary, secondary, or tertiary? Got a couple of people blowing up chat. Got a couple of people blowing up chat. Several people blowing up chat. Y'all all wrong. You're all wrong. It's not tertiary. It's not tertiary. It's primary. Why is it primary? Because in this case, these are chlorines attached to only a carbon, and that carbon is, that's the only the chlorines are what's attached to that carbon besides this thing here. And so this is essentially this type of picture where I've got 3 chlorines at the end of a carbon. Now, had these chlorines been something else, CH3 groups, now your answer should be, this is a tertiary substrate. Does that make sense now? Why won't this carbon do substitution? Let's see if we can remember that from just a few minutes ago. No, apparently not. Nobody typed it in chat. So the hybridization in this case is sp2, and just recall that sp2 hybridized carbons don't undergo substitution reactions. What about this substrate? Is this primary, secondary, or tertiary? Everybody's chat shy now that I told them they were wrong. It's not sp2, that's right. This one is sp3 hybridized. Let's think about how many carbons it's attached to. So we're not actually asking how many carbons, we are actually asking how many carbons is the red carbon attached to. And so let's count. 1, 2. And so that's a primary substrate. Or excuse me, that's a secondary substrate. My apologies. All right, so identifying substrates is going to be crucial. So if the carbon is at the end of the molecule and thus only attached to one other carbon, it's primary. If the carbon is in the molecule and then attached to 2 other carbons, it's secondary. And if the carbon is in the middle of the molecule and highly branched, attached to 3 other carbons, it's tertiary. So I'll just pause real quick, see if there's any questions about that. If not, then we're going to move on. Oops. All right, so let's think about this. So now what I want to get into is the Sn2 mechanism. And so we've already discussed the only other mechanism up to this point that you really have to know, quote unquote know, is the acid-base mechanisms. And you sort of already know that in the sense that acid bases react through proton transfers. And so or nucleophilic attacks, whether it's Lewis acids or Bronsted-Lowry acids. Bronsted-Lowry is proton transfers. Nucleophilic attack is Lewis acids. And so you already know those in the sense that those both represent one of the types of mechanistic moves. But this is the first reaction mechanism that you have to know in the sense of all of the possible mechanistic moves. Now, this is a good place to start when it comes to mechanisms, because at the end of the day, there's really only one step. Now, an Sn2 reaction happens with the word 2. We use the word bimolecular, and that's what helps you remember what the mechanism does or how the mechanism works. 2 means bimolecular, and bimolecular means that the reaction is concerted. And by concerted, what I mean is that the mechanistic steps that make up the reaction happen simultaneously. So the mechanistic steps happen at the same time. And so here are the 2 mechanistic steps that are involved in this reaction. There's only 2, and they happen at the same time. its nucleophilic attack and its loss of a leaving group. And if we think about it, if the reaction means something like this, where the nucleophile gets substituted for the leaving group, then those two mechanistic steps make sense. The nucleophile has some electrons or electron density. It attacks the substrate and it replaces the leaving group. And so the way the mechanism works is that, I'm going to use red. The nucleophile attacks the partially positive carbon at the same time remember, concerted. At the same time that the leaving group leaves. So this is it. This is the mechanism. This is the extent of the Sn2 mechanism. You now know it. You're now responsible for it. And if I show you any particular reaction and tell you it's an Sn2 mechanism, then you should be able to draw these two arrows out. Remember, at the bottom line is that an Sn2 or any bimolecular reaction is concerted. It happens at the same time. Does anybody have any particular questions? All right. One student says, nope, it all makes sense to me. Okay. All right. So now we're going to start to get in the weeds a little bit. When we think about chemical reactions, after we've decided what the mechanism is, that mechanism leads once we've decided what the mechanism is, that decision leads us to a few other questions. What is the stereochemical outcome? This is a new word. We're going to talk about it in a second. Regio. R-I-E, I think. Nope, maybe no I. We also want to think about kinetics. We also want to think about solvent effects. And those are really essentially the four major considerations that we want to make with any particular reaction. And so I'm sorry to stutter there for just a second. Hold on a second. All right. And so what we want to do first is I want to talk about stereochemistry first. So we're going to do an Sn2 reaction. And what I want to know is what's the stereochemical outcome of the reaction. So the first thing I want to do is go back to my S2 chlorobutane and let's have it do a substitution reaction. It's going to have the nucleophile attack that carbon. The leaving group is going to leave, and we're going to substitute the leaving group for the nucleophile. But because this is S2 chloropropane or chlorobutane, we want to point out that in this reaction, there is a stereochemical difference in the product. At this point, we decided that this was an S configuration, and let's remind ourselves what's going on here. The nucleophile is still going to be priority number 1. This is still going to be priority number 2. This is still priority number 3. The arrow still apparently moves around the counterclockwise direction, but now the hydrogen, instead of being away from us, is towards us. So what we'll do is we'll reverse our specification and say, did I do this wrong the first time, guys? Oh man, looks like yeah, thanks Aaron, appreciate it. So let's try this. So you're gonna have to go back and think about this. This one was R. This is still R. We'll reverse our answer to S. So at the beginning of the video, I'm not going to edit it. It's definitely just going to be wrong. It's going to be another bit of embarrassing bit on YouTube for myself, but that's going to be fine for later. I'll make a little note that that was incorrect. But at the end of the day, what happens to the stereochemistry? The stereochemistry is inverted. So when I'm thinking about what I'm talking about with, when you say supposed to be reversed, I want to make sure that I understand your question. Because hydrogen in the product is pointing towards us, whatever configuration we get, whatever arrow we get, and it was just, I drew the correct arrow last time, I just called it the wrong thing. Whatever arrow we get, because the hydrogen is pointing towards us, we just switch the designation. So we say that the arrow is R, but because the rules for specification require that the lowest priority group be pointing away from us, we have to switch our designation because that priority group is actually pointing towards us. Now we could always redraw the molecule, but that's a little bit more complicated than just saying, okay, reverse your answer. Again, at the beginning of the video, I have the arrow correctly, I just call it the wrong thing. On the other hand, when I'm talking about the stereochemical outcome of the mechanism, what we say is there is an inversion in the stereochemistry. So if the substrate is R, the product will be S. If the substrate is S, the product will be R. And so what I want to do is I want to talk about why this is, because this is an important part of the learning here, is to figure out what's going on with this and why the stereochemistry would be inverted. And this is going to lead us into this first consideration of what a transition state looks like. The reason why the stereochemistry gets inverted is that when I think about where this nucleophile attacks, we say that there is a backside attack. And what I mean from that is that if I think about the molecule from the perspective of the leaving group is on the front side and the nucleophile attacks on the back side. Now let's think about why that might be. Remember that the leaving group is partially negatively charged and the carbon is partially positively charged. And that's why it is reactive. Remember that the nucleophile either has electrons or it has a negative charge. And so when I think about the situation of the molecule, how the different species are oriented in a solution, the majority of the nucleophile will already be oriented in a position away from the leaving group and near the carbon that's positively charged. And so we get this situation where the nucleophile is naturally attracted to the positive charge, but it's attracted to that positive charge on the side that's away from the negative charge that's repelling it. And so now what I want to do is I want to talk about this transition state, because it's important to figure out what the transition state looks like. Remember that we symbolize transition states with a double dagger. And so what I want to do actually is draw a picture of the transition state. Well, what's involved with the transition state? I've got this carbon, and the hydrogens on the carbon are not changing position. Or in other words, those bonds don't break. But what bonds do break? The bond to the bromine has to be coming off. So I'm going to draw it with some dashes to represent that it's a partial bond. The same thing is going on with the bond to the nucleophile. It's starting to form. So I'm going to represent that with a partial bond with some dashes as well. So if I were to think about the structure of the transition state, what's going on here is that the tetrahedral configuration of the carbon that's being attacked becomes essentially trigonal bipyramidal, where this part of the molecule becomes planar. So this is a plane. Now, what happens as the reaction proceeds? As the reaction proceeds, the bromine comes off and the nucleophile is attached. So the question is where do these hydrogens end up? Do the hydrogens end up back here towards the nucleophile? Or do they end up over here where the bromine has left? And of course, the answer to that question is we're going to go where there's the most room and the most, and remember, because electrons will want to repel themselves. So the bonds will not collapse against the nucleophile. They'll move away from the nucleophile. So they don't move here. They do move over here. And so when I think about the resulting structure of the molecule, these hydrogens have moved to this position, and the nucleophile is attached on this and physically on the other side. And so this is a demonstration, this is an illustration of the inversion in the stereocenter and why it is, and why that inversion happens. And so one of the new things that we just learned today, right now at this moment, is to draw this transition state. And so one of the skills that you're going to have from the perspective of Sn2 reactions is drawing pictures of this transition state. And so remember, the transition state will involve partial bonds. It'll involve a partial bond of the leaving group leaving, and so that bond is breaking, and it involves a partial bond of the nucleophile attacking and becoming attached, so that bond is forming. The atoms that are in the middle, in the plane, they're not having bonds breaking or forming, and so they're sort of just getting out of the way and letting all this stuff happen. And so what I want to do is I want to stop right there and take a beat and see if there's any questions, if anybody has any questions. So throw them in chat if you got one. Okay. So real quick, if you got a piece of paper out and a pencil or a pen, let's go ahead and let's do a quick practice problem. What if I have something like this? And I react it with hydroxide. Let's do two things. let's do three things. Well, two things. What's the product? But you have to include the stereochem, and then what's the mechanism? And so at this point, I'm going to just wait for just a few seconds to let those who are still sort of with a piece of paper, who have a piece of paper and a pencil out, to think about how that works, to kind of give you an idea of what's going on. Let you practice that. And then we'll go ahead and solve it. So what is the product? Well, remember that the product involves essentially the same substrate, but it involves a substitution of the leaving group with the nucleophile. This is the leaving group. This is the nucleophile. So what I want to do is I want to substitute those two groups. But remember, I have to include the stereochemistry. And one of the things that I have to remember is that the stereochemistry is inverted. So if I draw the molecule the same way, then instead of drawing a wedge to represent the bond up to the leaving group coming towards me, I want to draw a dash to represent the bond to the nucleophile going away from me. So this is the resulting stereochemical outcome. And if I want to, I can draw the hydrogen here. If I want to, I can draw the hydrogen there. So this would be, so the question is asked, isn't OH a bad leaving group? And the answer to your question is, yeah, it's a terrible leaving group. But in this mechanism, in this particular reaction, is it acting as a leaving group? And the answer is no. Remember that the leaving group is on the substrate. This thing is the nucleophile. Is OH a good nucleophile? And the answer to that question is yes. It has lots of lone pairs of electrons. It has a full negative charge, so it is quite attracted to the partially positive charge of the carbon. And so the last little bit, we've got this piece. Now let's draw the mechanism. And so all I need to do is draw one arrow showing the nucleophilic attack. And then I show the other arrow for the loss of the leaving group. And remember that since the reaction is concerted, it happens at the same time. So I show both of those arrows at the same time. So the question is asked, did it start off as an R configuration and change to an S? And so let's try this. Let's make sure that Cotton can do it right this time. And so let's try to specify the configuration correctly. So that's 1. This is priority 2. This is priority 3. The hydrogen is priority 4. It is pointing away from me. And so if I do this arrow, I get 1, 2, 3. And let's see if I can do this. This is counterclockwise. That's R. I'll let somebody correct me if I'm wrong, but I think I got it right this time. So let's try this one. This is priority number 1. This is priority number 2. This is priority number 3. Hydrogen is still priority number 4. I get the same arrow, but because hydrogen is pointing towards me, I say that I actually need the reverse direction of the arrow. So the actual configuration is S. So the answer to the question is yes, the R configuration in the reactant changed to the S configuration in the product. Any questions about that? The question is, do we always reverse the configuration? And the answer to that question is yes. When you're dealing with an Sn2 mechanism, the configuration of the stereochemistry is always reversed. Now, that means there has to be a stereocenter, right? If I have a chlorine attached in the middle between two CH3 groups, we would like to point out this is not chiral, right? So there's not 4 different groups attached to it. So even if I do a reaction where there's a nucleophile that gets replaced, I don't need to show the stereochemistry reversing because there isn't a stereocenter. Does that mean that it doesn't go through a trigonal bipyramidal transition state? No, that's not what it means. It just means that since the transition state is there isn't a chiral center in the reactant and there isn't a chiral center in the product, the specification of the stereochemistry is not necessary. And so the answer to the question is yes, it's always reversed, but we only have to specify it when there's actually a stereocenter. All right, good stuff. All right, so let's think the next thing I want to consider about this reaction is the kinetics. In other words, the speed of Sn2 reactions. And what I'm going to look at is the substrate. Well, one of the substrates that I showed you was a methyl alkyl halide. The other substrates are primary, secondary, and tertiary. And so remember that a methyl is simply a CH3 with an X. A primary would be something like that. A secondary would be something like that. And a tertiary would be something like this. And so there is an order of preferential treatment when it comes to the substrate. It is faster in this direction. Take a minute to kind of think about why that might be. Why might the methyl reaction be faster than a primary, which is faster than a secondary, which is faster than a tertiary? If I say this, let me say this. Let's go ahead and let's give this, let's say if I want to talk about relative rates. If I assign a relative rate of 1 to the primary substrate, it's not, so the thought is maybe methyl is less stable. It's really not about the stability. And so let's think about what actually might be going on here. If I assign 1 as a rate for the primary, methyl is about 150 times faster. What happens to secondary? Look how slow it is. It's almost 1,000 times slower. And this one is so slow is that it can't be measured. In other words, it essentially doesn't happen. Sn2 reactions essentially do not happen at tertiary substrates. And so let's think about why that might be. When we think about the reasoning behind the kinetics of the reaction, what we want to think about is what is the mechanism and what's involved in the mechanism. If I put this in the corner so that it's not in the way, but it's not forgotten, let's think about this methyl substrate. And let's do it from this perspective again. If I have a nucleophile, and let's go ahead and make it hydroxide, and it comes in to do a backside attack, it essentially has to get around these hydrogens. So what's really driving this kinetic consideration is something called Sterics, and we've already sort of been introduced to this concept. When we thought about the relative stabilities of cycloalkane or cyclohexane chair conformations, the 1,3-diaxial strain is a type of steric interaction. This steric interaction raises the energy. And so what happens as I start to think about this in terms of an energy graph? What happens if I start to replace these hydrogens with other alkyl groups? Now I'm providing an additional bit of steric hindrance, because if I think about it and I really draw out this CH3 group, it's tetrahedral and these other hydrogens are in the way. So what happens when I do that? If I think about this CH3 group, I've raised the activation barrier just a little bit. I've raised the activation barrier just a little bit because I've got a little bit more stuff in the way. Now this graph is not the same products. It's not the same reactants. We're going to ignore that for the time being because I want to just draw this on the same graph. But if I continue to do this and I continue to replace CH3 groups with other alkyl groups, then I continue to provide more essentially stuff in the way, and I continue to raise the activation barrier. And by the time I get to the point where I've added 3 different R groups, it's now so crowded, the activation barrier is so high that it essentially doesn't happen. And so when we think about the kinetics of an Sn2 reaction, we recall that it's related to the substrate. And we say to ourselves that the less sterically hindered the substrate, the more favorable an Sn2 reaction is to occur at that location. The reason that the substrate favors a less hindered reaction or a less re-hindered location is because there's more room for the backside attack to occur. And at the end of the day, it really is a conversation about the mechanism. Since the mechanism is concerted, that this happens, that the attack, the nucleophilic attack, happens at the same time as the loss of the leaving group, this substrate has a huge effect on the kinetics of the reaction because it really does change the energy of the transition state. And as you change the energy of the transition state, you're raising the activation energy. Okay. Anybody have any questions about that? I'm going to pause just a beat. All right, cool. All right, so there's another consideration that I want to make. And that consideration is I want to consider oops, 1L. All right, so this is the consideration that we want to make. What else affects, contributes to nucleophilicity? It's a word. I didn't make it up. Klein didn't make it up. Some organic chemistry in the 1800s made it up, or some organic chemist in the 1800s made it up. And so what we want to consider is we want to consider the nucleophilicity of the nucleophile. Essentially, how strong of a nucleophile is the reagent. Let's consider hydroxide versus water. Do you think that they're both nucleophiles? What do you need in order to have a nucleophile? You got to have electrons. The electrons have to be able to attack. And so one student answered, yeah, they're both nucleophiles. And in fact, they are both nucleophiles. But one of them is stronger than the other one. And why might that be? This is the stronger nucleophile, and this is the weaker nucleophile. And the long story short is that the more negative a species is, the stronger its nucleophilicity will be. The better at acting as a nucleophile the better at acting as a nucleophile it will be. And so it's not that a substitution reaction or an Sn2 reaction won't occur with these two species. It's just that one is going to be more favored over the other. And at this point, all you really should be able to do is identify the strength of a given nucleophile. Later, we're going to complicate it. We're going to actually start to talk about whether or not it's a nucleophile, whether or not it's a base, whether it's strong, whether it's weak, whether it does both things, whether it's both a nucleophile and a base, and whether it's going to do SN1, E1, E2, and SN1. We're going to have all four mechanisms all tied up together, and we're going to have to decide between all four. But right now, we're still squarely in the SN2 regime. And so the only skill right now you should be able to do is identify the strength of a given nucleophile. And so let's just try this real quick. What about chloride versus ammonia? Which one's stronger? Which one's weaker? Well, it works really well. It works really well in class. Uncomfortable silence works really well in class. It doesn't work so well on Zoom. There we go. There's a few. Yeah, chlorine's stronger. This one's weaker. And so here's some strong nucleophiles. And of course, these are in the slides. So you can go take a look at that on Blackboard. Here's some examples of some strong nucleophiles, of course. I-, Br-, Cl-. Here's some other nucleophiles. SH-, OH-. If you have an R group attached to a negatively charged sulfur, that's also a good nucleophile. Same thing would be true if you had an R group attached to a negatively charged oxygen. That would also be a good nucleophile. This is a nucleophile that you should be familiar with. And if you're not, you need to become familiar with it. Cyanide, anion, is a very good nucleophile. Weak nucleophiles are generally things that are neutral, like water, alcohols, and thiols. They're definitely weak nucleophiles. And so your job right now is to essentially be able to classify things as strong or weak nucleophiles. Okay. Questions about that? All right. Here's a little bit more of a challenging topic. How does the solvent choice affect the actual kinetics of the reaction? how does the solvent affect the rate of the reaction? And so here's what I'm going to tell you first is you need polar aprotic solvents favor Sn2 reactions. So in order to do an Sn2 reaction, you need a polar aprotic solvent. And so what does aprotic mean? Well, protic involves a proton, and aprotic means that the solvent doesn't have a proton. And so let's think about some aprotic solvents. Something like acetone, something like dimethyl sulfoxide, something like acetonitrile. Notice there are no acidic protons on any of these species. DMF, dimethyl formamide. What's an example of a protic solvent? First one to type it in the chat gets 100 on the exam. Too late. No hundreds today. Oh, there we go. Stereochemical is not a solvent, Karen. Water would be an example of a protic solvent. An alcohol would be an example of a protic solvent. Anything where you could imagine that the hydrogen is somewhat acidic would be examples of protic solvents. All right. So now, so you've learned some trivia. The trivia that you've learned is for Sn2 reactions, you need a it's coming. You need a polar aprotic solvent. All of these solvents are both polar, but they don't have any sort of acidic protons. Why though? That's the trivia that you've learned, and you should be able to sort of then identify some. Acetone. This one is dimethyl sulfoxide, DMS. This one's this one is, excuse me, one more time. This one is DMF, dimethyl formamide. Right? And so now that you've identified the trivia part, the question now is, and this is my favorite question on exams, is why? Why do polar aprotic solvents favor Sn2 reactions, and why do they actually make the reaction rate happen faster? And so what I want to do is I want to draw an energy graph. So let's think about a polar aprotic. Let's think about a reaction where I'm going to have a substitution. And I want to actually write out the reagent, sodium hydroxide. And the product will be OH. Of course, I'm not showing the stereochemical outcome because that's not an important consideration right now. So let's think about what's going on with the solvent if it's something like DMSO. Why would this favor the formation this reaction? Why would it favor the Sn2 reaction? And so what we really need to do is think about all of the species that are in the solution. First of all, I have sodium hydroxide, or sodium, and I have hydroxide. How would a solvent that's polar, like this thing, interact with the two species that are in solution. Well, let's think about the different pieces of this. The oxygen has some lone pairs of electrons. It's more electronegative than sulfur. And so sulfur is partially positively charged and the oxygen is partially negatively charged. So when I think about it, I want to invoke Sterics again. When I think about it, I can say to myself, well, because the oxygen is partially negatively charged and that those electrons are available, they're unhindered, then what this means is that a species like the sodium ion is stabilized or is able to interact with molecules of the solvent, right? What about the hydroxide? Where would the hydroxide want to react? The hydroxide wants to interact with this positive action. Yeah, exactly. It wants to interact with the sulfur. But there's a problem here. What's the problem? The problem is there's no room. That sulfur is hindered. Yeah, it's not that the word isn't full, the word is hindered. It's sterically hindered by the R groups that are attached to it. So yeah, the sulfur is partially positively charged, but I can't get around here. This isn't a good interaction because that's negative. I can't get in here to the positive charge on this side because I'm hindered by the two CH3 groups. So what we say is this leaves the nucleophile bare, unstabilized. And so when I think about this from a polar aprotic solvent perspective, we're going to see that the energy of the reactant is higher than with a polar protic solvent. So let's take this same perspective and let's do the same thing with something like water, which is a polar protic solvent. So let's think I still have some hydroxide in the solution and I still have some sodium ion in the solution. Well, how is the sodium ion going to interact with the water? Well, the lone pairs on the oxygen will interact with the sodium ion and stabilizing the sodium ion just the same way that the polar aprotic solvent did. But take a look at the hydroxide ion as it interacts with water. The positive part of water are these protons. And so there's no problem with the protons getting in here and interacting with the hydroxide ion, forming the same stabilization. Because both the nucleophile and its counter ion are stabilized, comparatively speaking, they're lower energy. So if I have a protic solvent versus an aprotic solvent and the same species, what have I done to the activation barrier? How have I changed the activation energy? The polar protic solvent provides a large activation barrier. Compared to the protic aprotic solvent. So to summarize, when I have a polar aprotic solvent, the energy of the reactants actually increases, or it's larger. Because the energy of the reactants is larger and I'm going to the exact same transition state, the activation energy is smaller. When I use a polar protic solvent, I'm stabilizing both the counter ion, the sodium, and the nucleophile. So the activation energy in that case is larger because the actual reactants have a lower energy. They're stabilized through this interaction. And so this is a situation, up until this point, we've been saying to ourselves, stability is good. Stability is something that is good. In this case, when I'm thinking about an Sn2 reaction, the extra stability brought about by a polar protic solvent makes the reaction unfavored. And so this is a kind of something that's sort of a new thought. Well, does instability lead to something that we consider to be favorable in a reaction? And yeah, it turns out it does. Instability with an aprotic solvent leads the nucleophile bare and unstabilized. It's ready to react. Okay. Anybody have any questions? I'm taking a full minute to stop there because I want to switch gears. We still got at least about a half an hour, and so what I want to do is talk about E2 reactions. Okay. All right. So we just finished talking about substitution reactions when it comes to Sn2, nucleophilic substitution, and the 2 means bimolecular. E in this case means elimination. What does the 2 mean? Still means bimolecular. So when I thought about a substitution reaction being bimolecular, it meant that the reaction is happening, the 2 mechanistic steps are happening at the same time. The loss of the leaving group was happening at the same time as the nucleophilic attack. That led to all these interesting properties that we discussed. The inversion in the stereochemistry. It led to the relative reactivity of the different substrates, and that was an important piece of the consideration for this reaction. It's also going to be important for E2 reactions. So bimolecular, just like before, still means that the reaction mechanism is concerted. It still means that the mechanistic steps happen at the same time. But remember, there's a difference in what the results and what the reagents are. In this case, what we do is we form an alkene with a base. And so the mechanistic moves are different. One mechanistic move is the same. There's definitely still a loss of a leaving group. But the other mechanistic move is proton transfer. So it's probably somewhat confusing for me to write 1 and 2 because really it's only one step and both of these mechanistic moves are happening at the same time. And so in order to show this mechanism, we're going to need to draw the protons that are getting transferred. So recall that there's 2 protons here. What happens is the base does the proton transfer at the same time as the electrons that were attached to the proton form the double bond, which kicks off the leaving group. And so this is still two mechanistic moves: proton transfer, loss of a leaving group. Remember that proton transfer requires two arrows, and the loss of a leaving group requires its own arrow. So the next level of difficulty in this today's lecture is that we're adding we have three arrows, but all three arrows are happening in a concerted fashion. The product in this reaction is an alkene. Okay. All right. So any questions up to this point? Because now, at this point, what I've done is I've entered. The question is asked, is that for all elimination reactions? That it does all, in other words, the question is, do all elimination reactions produce alkenes? And the answer is yeah. Both E1 and E2 reactions have alkenes as their products. The difference is the mechanism by which it does that. In E2, the reaction is concerted, it's bimolecular. The loss of the leaving group happens at the same time as the proton transfer. What we're going to learn is that in unimolecular reactions, Sn1 and E1, that's not concerted, they're stepwise reactions. The mechanistic moves happen in their own individual steps. But at the end of the day, the answer to your question is yes, all elimination reactions produce alkenes for our consideration. So when I want to think about it, I want to think about the same sort of situation. Or I want to make the same considerations with E2 that I did with Sn2. In other words, what would be the effect of the substrate? So in an Sn2 reaction, we said that the substrate is has a big effect. The Sn2 favors an unhindered substrate. But what about a hindered substrate here? Let's try something like this. Do you think this reaction is favored or unfavored? Is there a steric hindrance consideration for the ability of the base to function in order to form the alkene? Let me redraw the substrate, and let's actually show the mechanism. Remember that the proton transfer happens at the same time as the loss of the leaving group. So what's happening? What's the action here? The action is that we have a base, and the base in this case is doing a proton transfer. What if I actually specify the base? What if we come in here and we say, okay, the base is hydroxide ion. We showed hydroxide ion acting as a nucleophile, but remember, hydroxide is also a base. And so the base, hydroxide, is the first sort of example where you have something that could be both a base and a nucleophile. Well, what did we say the problem with hydroxide acting as a nucleophile was? If we try to have hydroxide act as a nucleophile, oh, there's too much hindrance here. So it doesn't really act as a nucleophile. because we have a tertiary substrate. There's too much steric hindrance for the hydroxide to react as a nucleophile. But is there a problem with the hydroxide acting as a base? And the answer to the question is no, there's no problem. Because even though the carbon itself, this carbon, is hindered, are the hydrogens doing the proton transfer hindered? And the answer to that question is no. These hydrogens are sticking out in the open. There's nothing that's preventing the hydroxide from doing a proton transfer. So when the substrate is hindered, you don't have a problem with an E2 reaction happening. Does that mean that there's a problem with an E2 reaction happening when it's primary? No. There's no problem there either, because these hydrogens are still not hindered. So substrate effects are quite different with an E2 reaction in the sense that there aren't as many substrate effects on an E2 reaction. For E2, the substrate really doesn't matter so much. But we saw for Sn2, the substrate really was a big deal. So what I want to do is I want to stop right there and pause a nice little beat to decide whether or not anybody's got some questions. All right, so I think what we're going to have enough time for the rest of the lecture today is to talk about something I'm sure you're all excited to learn. What's the name of these products that we're going to form? We're forming alkenes. We've introduced alkenes for the first time. We haven't talked about what their names are and how to name them. And so that's what we're going to do for the next bit. And that'll what we'll do to wrap up the lecture. Okay, so what is this particular species? Well, we're still going to count carbons. So at the end of the day, boys and girls, we've got 1, 2, 3, 4 carbons. And so what's the suffix for 4 carbons? Bute. Yeah. But it's not an alkane anymore. It's now an alkene. So we want to say that it's butene and not butane. But now there is actually a consideration to make. That's butene. That's butene. And that's butene. We need to be able to specify the differences between all of these things. Yeah, and so the thought is, one, you have to specify the location of the double bond, and you have to specify the stereochemistry. Remember, there is no free rotation around a double bond. So these two guys are not the same. These are stereochemical differences. They have the same connectivity, but a different three-dimensional shape. And so we're going to have to deal with that. So the first thing, though, is locating the double bond. How do we locate a double bond? Well, we're still going to choose the longest chain, but in this case, the chain has to include the double bond. So we're still going to choose the longest chain that includes the double bond. And then we number in the direction that gets us to the double bond as fast as possible. So we could have numbered it 1, 2, 3, 4, but that numbering sequence is incorrect. The numbering sequence shown before, where I number the double bond at number 1, that's the correct numbering pattern. So in this case, you have two different choices. Choice number 1 is to call it 1-butene. You don't say 1,2-butene because it's already implied that the double bond is between two carbon atoms, the one and its adjacent atom. So I only need to tell the reader where the double bond starts. I don't need to tell the reader which two atoms connect the double bond because that's already implied structurally. So the first choice is to call it 1-butene. But you'll see later on as you get more experience why I prefer the second choice. You can also say but-1-ene and to tell the reader where the ene actually is and sort of break up the root of the name. While this does seem simpler at the moment, this one is a little bit more structurally straightforward. So I think it makes a little bit more sense in the long run. And we'll see why that is in a bit. Well, what about these two guys? They're both butenes, but where do I number from? Well, in both cases, I would number from, it doesn't matter which side I number from because I get to the double bond in the same space. So it's going to be 1, 2, 3, 4. Could still just be 1, 2, 3, 4. In either case, I get but-2-ene. And I'm only going to use this example from now on. So remember that you can do this one, but from now on in lecture, I'm only going to use this version. So yeah, we've got but-2-ene, but both of them are but-2-ene. And so how do I specify the difference? What is the difference here? This one's trans, this one's cis. And that should make some sense to you guys at this point because you already have cis and trans experience with cycloalkanes. When the two groups on either side of the double bond are facing the opposite directions, that's trans. When they face the same direction, that's cis. Stop me if you have any questions. Let's try something like this. What's the name of this molecule? Well, when we thought about alkanes, we would have said to ourselves from alkanes, we would say, let's number the direction that gets us to a substituent the fastest. But this numbering scheme is actually not correct. And the reason it's not correct is that a double bond has a higher priority than any single bond. And so the rule is to number from the direction that gets you to the double bond the fastest. So it's actually should be numbered this way. But everything else sort of happens at the same way. And so we're still going to talk about the different substituents and where they're located. Now I've got 1, 2, 3 methyl groups. So that's trimethyl. So I have a trimethyl. Where are they? They're at 5, 5, and 6. So I have 5, 5, 6 trimethyl. And what is it? It's 5, 5, 6 trimethyl. It's a heptene, and it's hept2ene. And then there's one piece of information we need. It's trans. That's right. That is the other piece of information. So putting it all together, stereochemistry in front, then the list of substituents as normal. And then you've got your name. So let's think about cis and trans here for a second. Check my time. I got about 9 minutes. So what is this? What's this one? So the question was, why is it trans? Aren't they both pointing downwards? And if I remember correctly, the structure we were looking at was something like this. With this was an R group and this was a CH3. It's trans because in general, we can say this group points this way and this group points this way. The cis version would have looked like this. Okay. So what's this one? The one at the top left-hand corner, that's trans. What's this one? Cis. What about this one? At the end of the day, cis and trans fail here. Yeah, I wanted to give you guys some opportunity to kind of put things in chat to kind of think about it for a second. But at the end of the day, cis and trans don't make any sense because at this point, one of the things I can look at is like, oh, I've got some hydrogens attached right here. We can talk about the groups, even if they're different. These two groups are the same, but these two groups are different, methyl and an ethyl. Well, we can say, well, what's trans? What's pointing in opposite directions? Well, we can say the hydrogens are pointing in the opposite direction. Same thing here. We can say the hydrogens are pointing in the same direction. But what about in this case? It turns out that there aren't two identical groups to get a cis or trans designation. So we're going to have to learn a completely new way to specify the stereochemistry. And so what I'm going to do for the next 5 minutes is introduce that stereochemistry, or introduce that configuration method, and then we'll pick it up there on Thursday, and we'll start with this. We'll do some more examples, and we'll move on with Sn1 or Sn2, E1, E2, and Sn or an E1. And so this is the nomenclature that we want to learn. It's really easy. That was funny, right? Ha, ha, ha. It's easy. All right. So let me show you what we mean by EZ. E and Z are abbreviations for German words. And if I can remember how to spell them, It's entgegen and zusammen. These words mean together and apart. And what are we thinking about? What's either together or apart? It's going to be the group we assign high priority. And we already have some experience assigning high priority groups. We're going to do it the same way that we've done before, and it's going to be based on molar mass. So what I mean by assigning high and low priority is what we do is we take the double bond and we split it in half. And now what I'm going to do is I'm going to choose based on this half and based on this half, I'm going to choose the high and low priority group on each half. I'm going to assign a high and low for one. I'm going to assign a high and low for two. And then I'm going to decide whether the groups that we assign, and that's an N, by the way, not an H, high and low priority, whether they're going to be entgegen, apart, or zusammen, together. And so we're going to assign it based on mass. Assign right? And it's just like we did when we're assigning for stereochemistry and chiral centers. The higher the mass, the higher the priority. But in this case, it's only going to be high and low. We don't need different numbers because we're going to assign a high and a low for both 1 and 2. So in this case, we're going to give the low priority to hydrogen and the high priority to nitrogen because nitrogen heavier than hydrogen. Then we're going to come over here and we're going to look at this and we're going to say carbon versus fluorine. So we get a low priority for carbon and a high priority for fluorine. The two high priority groups they're together. They're both down in this case. But remember, down is just subjective because they could have oriented the double bond differently. In other words, they're together. And so this is the Z version of the molecule. If I were to redraw the molecule, and swap the position of the ammonia group, I would get high priority here, low there, high here, and low there. And now we would say, the high priority is apart or opposite from the low the high priority groups are apart from each other. And so this is the E version. And so what I'll do is we'll say, okay, let's take that. Let's use this. I'm just going to erase it since I flipped it. And let's do our last thing and let's let this example be our last naming example. Okay, so let's go through all the steps. Let's number the longest chain. So the longest chain has to include the double bond. So one option would be to go that way. How many carbons does that have? 1, 2, 3, 4, 5, 6. Another option would be to go this way. How many carbons does that have? 1, 2, 3, 4, 5, 6, 7. So which one is correct? Is it yellow or blue? Well, it's going to be blue because blue has 7 carbons and yellow had 6. So now I can number it. Is it 1, 2, 3, or is it 1, 2, 3, 4? Well, it's the first case because that gets me to the double bond at the 3 position rather than the 4 position. So it's 1, 2, 3, 4, 5, 6, 7. So let's identify the different groups that I have attached to that chain. I have this group, and this group. This one is a 1-methyl ethyl, just like before. This one is a methyl group, and this one is a chloro. Almost done. It's a heptene. Oops. And we know that it's a hept3ene specifically. And now we need to figure out if it's E or Z. So now we have to assign priorities. Well, when I do this double bond in half, the chlorine is higher priority than the carbon because it's heavier. And then which one of these groups is higher priority? Is it the group that is on the bottom or the group that is on the top? We're going to have to decide the same way that we had to decide with chiral centers. In other words, we go here and we get a carbon. And here we get a carbon. It's tied. So we continue to look out along the chain. I have a CH3 here and a CH3 here. So that's no help. On this side, on this branch, I have a CH3, but on this branch, I have a CH2. And that CH2 is connected to another carbon. So because this group has more carbons in it, and I break the tie by saying the only thing that the tied carbons are attached to at the top are hydrogens, but I have a carbon that is breaking the tie at the bottom group. And so for this case, I have high priority here, low priority there. So this is the Z version. The top is actually the lower priority group because of the tie breaking. This is the high priority group because this carbon breaks the tie. So it's Z, and so now I'm going to put it all together. So I have Z. This will be the last little bit. Z, and now in order, what is it? 3 chloro. What comes first, methyl or methyl ethyl? Methyl. 5 methyl, 4 1-methyl ethyl. And then I'm going to put it all together now. Hept3ene. So I ran out of room on my screen, but if you would put it all together, then it would all run together as one long name. All right, that gets us to 11:04. We went a little bit further. Appreciate everybody sticking with me. What I'm going to do is I'm going to stop the recording. If you want to stick around and ask questions, feel free to do that.